Hello friends, in this video I'd like to solve the following problem from the Romanian International Mathematical Olympiad Team Selection Test 1996, problem 11. We wish to find all primes p and q such that k to the power 3pq minus k is divisible by 3pq for all integers k. It's a nice problem from number theory, a bit complicated. Here are my hints for this problem. Let's put it in the right place. Okay. Here are my hints. First of all, we'll use the following fact that group ZP star, which consists of numbers from 1 to p minus 1 with the operation of multiplication modulo p, this group is cyclic, which means that there is some element which generates this group, which in turn means that the order of some element alpha modulo p equals p minus 1. And you may ask, what is the order of an element? Well, the order of element alpha modulo m is the least exponent k such that alpha to the power of k is congruent to 1 modulo m. It's the least positive exponent. And another important fact, recall that if alpha to the power of L is congruent to 1 modulo m for some positive integer L, or to be honest, for every integer L, then the order of alpha modulo m must divide L. Powerful fact, we'll use it. And you may assume without loss of generality that p is less than or equal q, and you should try to establish these two results. And at some point, well, one of these says that 3p minus 1 equals a q minus 1 for some integer a, and you should think about what are the possible values of a. There are not that many. And you may also wish to use Fermat's little theorem at some point. So give this problem a try, and I will see you in just a minute. Okay, so here is my solution. Let's assume that p and q are primes, p is less than or equal q, and that our condition is satisfied, so that for every integer k, k to the power 3pq is congruent to k modulo 3pq. Let's assume that. Okay, and now groups zp star and zq star are cyclic, which means, i.e., that u to the power 3p, u to the power, or not, the order of some element u modulo p equals p minus 1, and the order of some element v modulo q is q minus 1 for some integers uv such that, well, GCD of u and p is 1, or let's write it in a simpler way, p is not divisible by u, u is not divisible by p, q does not divide v. Okay, and now let's plug in to our condition k equals u and k equals v. And we have the following. U to the power 3pq is congruent to u modulo 3pq, and v to the power 3pq is congruent to v modulo 3pq. But since these two congruences are true, well, these weaker congruences are also true. So u to the power 3pq is congruent to u modulo p, just p, and v to the power 3pq is congruent to V modulo Q. But that in turn, what does it mean? Well, since the order of U is P minus 1, U to the power P minus 1 is congruent to 1 modulo P, and V to the power Q minus 1 is congruent to 1 modulo Q. Which means that our system of congruences can be written because U to the power of P is congruent to U. So it's U to the power 3Q is congruent to U modulo P, and V to the power 3P is congruent to V modulo Q. And now, since U is co-prime to P and V is co-prime to Q, we may divide first by U, second by V, and we have, maybe let's write it in different color. U to the power 3Q minus 1 is congruent to 1 modulo P, and likewise V to the power 3P minus 1 is congruent to 1 modulo Q. Very well. Now, by the property of order, we know that the order of element U modulo P divides 3Q minus 1, and the order of element V modulo Q divides 3P minus 1. But what is the order of U? Well, it was by definition P minus 1. So P minus 1 divides 3Q minus 1, and Q minus 1 divides 3P minus 1. And you know what? These are so important that I will mark them. It's condition number 1, this is condition number 2. And I will use condition number 2. So by condition number 2, we have the following. 3P minus 1 equals Q minus 1 times A for some positive integer A. And now I wish to consider a few cases. First case will be the big case. Case number one, when A is greater than or equal 6. I will show that this is impossible. Why is that? Then let's take a look. We have a chain of inequalities. 3P minus 1 should be equal AQ minus 1. But A is greater than or equal 6. And remember, let's go back. Q is less than or greater than or equal P. So it's greater than or equal 6, P minus 1. Now, after some rearrangement, we will get that P is basically less than or equal 5 over 3, which is impossible. Which is impossible since P should be greater than or equal to. So okay, so now we have only cases of 1, 2, 3, 4, and 5. Case number 2, A equals 5. What happens then? If A equals 5, we have 3P minus 1 equals 5Q minus 1. 5Q minus 1, okay. But again, Q is greater than or equal P, so it's greater than or equal 5P minus 1, which after some shuffling means that P should be less than or equal to. P must be less than or equal to after some rearrangement. Okay, but the only prime which satisfies it, it's 2 itself. So now we know that in this case, P equals 2, and what is Q? Well, Q can be computed from this equation, On the left hand side we have 6 minus 1, 5. We can divide by 5. We'll get q equals 2 as well. Well, is it possible for this to be a case? Well, no, because that means that for every k, for every integer k, it should be the case that k to the power, let's go back, 3 times 2 times 2, 3 times 2 times 2 is 12, should be congruent to k modulo 12. And this is obviously not true. It's not true. It's false. For example, for k equals 6, should be pretty easy to see that it is false. So it's not a pair of solutions. Not a pair of solutions. Not a pair of solutions. Okay, let's consider the next case. Case number 3, a equals 4. A equals 4. What happens when a equals 4? When a equals 4, 3p minus 1 equals 4q minus 1. But again, let's play our estimation game. This is greater than or equal 4p minus 1. And after some shuffling, that means that p must be less than or equal, maybe let's write it in yellow, p must be less than or equal 3, probably 3. Yes, it is. Okay, so now we have what possibilities? Either p is 2 or p is 3. If p is 2, then what is q? Well, p is 2. No, p cannot be 2, because then if p is 2, then 2 does not divide 3p minus 1, but at the same time 2 should divide 4q minus 1. Impossible. Impossible. So it must be the case that p equals 3. If p equals 3, then q equals what exactly? Here we have 9 minus 1, 8. 8 divided by 4 is 2, and we add 1. Q equals 3. Q equals 3. Well, but here again we'll have some problem, because that would mean that for every integer k, it should be the case that k to the power 3pq 27 is congruent to k modulo 27, and it's simply not true. It's false. It's false already for k equals 3. For k equals 3, it's false. So k equals 3, k equals q equals 3, not a pair solution. Not a pair of solutions. Okay. Case number 4. Case number 4. Now we are considering a equals 3. A equals 3. Can a be equal to 3? Well, let's take a look. That means that 3p minus 1 equals 3q minus 1, and here we have contradiction immediately, because this is divisible by 3, this is as well, but this isn't. So it's impossible. Impossible. Because 3 divides 3p, 3 divides 3q minus 1, but 3 does not divide 1. Now, case number 5. I wish now to consider a equals 1 and leave the most important case for last. Case number 5. A equals 1. If a equals 1, then 3p minus 1 equals q minus 1, which means that 3p equals q. And this is impossible because q is a prime, and here we have a product of two numbers. Impossible because q is a prime, and q is a prime, and p is greater than or equal to. So it's impossible. And last case number 6, and last, a equals 2. A equals 2. Well, then 3p minus 1 equals 2q minus 1. And I will use one condition which was established along the way, namely, condition which I marked this condition, that p minus 1 divides 3q minus 1. So let's write it. By condition number 1, p minus 1 divides 3q minus 1. Is it right? Do I get it right? P minus 1 divides 3q minus 1. Okay, very well. And now, what will I do? Well, maybe let's put it a little bit lower. And now I wish to transform my equation a little bit. So I wish to multiply by 3. So I have 9p minus 3 equals 6q minus 6. And let's do what exactly? Let's add 4 to both sides, yes. 6q minus 2. 9p plus 1 equals 2, 3q minus 1. Okay, it's what I want. But now, remember that this number is definitely divisible by p minus 1. So, p minus 1 divides 9p plus 1. But also, most definitely, p minus 1 also divides 9p minus 9. Which means that if I add these two numbers if I subtract these two numbers together, p minus 1 must divide 10. And now we are left with just a couple of possibilities. Which primes reduced by 1 divide 10? Well, we have only a couple of options. 2, yes. 3, yes. 5, not. 7, also not. And 11. So p must be one of these numbers. P must be one of these numbers. And let's find q for each possibility. Well, if p equals 2, what is q? Well, let's copy it. Let's copy this condition. Well, if p equals 2, on the left-hand side I have well, I have a contradiction right away, because if p equals 2, then 3p minus 1 is odd, but the right-hand side is even. Contradiction. Let's move to case with p equals 3. If p equals 3, what then? Well, if p equals 3, then we have the following. 8 equals 2q minus 1, which means that 4 equals q minus 1, which means that q equals 5. But I will show that here we have a problem, because that means I will play the same game. That means that for every k, for every integer k, k to the power 3 times 3 times 5, which is 45, should be congruent to k modulo 45. But it fails, for example, for 15. So it is not true for k equals 15. So it's a contradiction. So 3 t, so t equals 3, q equals 5 is not a pair of solutions. Not a pair of solutions. And now I need a new page, so give me a moment. Very well. So the last possibility. If p equals 11, if p equals 11, what is q? Then we have, what exactly? We have 3p minus 1, so 3 times 11 minus 1 equals 2 times q minus 1. So we have 32 on the left-hand side. So we have q equals 17. So we have p equals 11, q equals 17. But the question is it really a pair of solutions? Well, now we need to check if for every integer k to the power 3 times 11 times 17, is it always congruent to k modulo 3 times 11 times 17? We have to check that. How can we do it? Well, let's notice that this condition, it is equivalent to saying that by the Chinese remainder theorem, saying that for every k integer k, our congruences are true modulo 3, 11, and 17 separately. So modulo 11 So we will check these three conditions. First one, let's take a look, because what is, notice that 3 times, well, each of them, so that holds, this first one definitely holds if, no, let's do it one by one, nice and easy. One, Roman 1, Roman 2, Roman 3. Let's check them one by one. 1. Well, well, it's so simple that we can check case by case. If k is congruent to 0, then k to this power is congruent to 0, so it holds. If k is congruent to plus minus 1, then k to this power, notice that the exponent is odd number, so it's congruent to plus or minus 1 as well. If we have plus, we have here plus as well. If minus, minus as well. So it holds. It's verified. Let's verify 2. Now I will not prove it case by case, but notice that if k is congruent to 0 modulo 11, then obviously k to this power is also congruent to 0 modulo 11. And if k is not congruent to 0, we can use Fermat's-Little theorem. And notice that k to the power of 10 is congruent to 1 modulo 11. And now, maybe let's also write it. What is 3 times 11 times 17? It's 561. So happens to be. So that means that if I raise both sides to the power 56, I have k to the power 560 is congruent still to 1 modulo 11. And if I multiply by 1, I have my congruence, which I want to prove. So it holds. And now, third and last, modulo what? Modulo 17. So if k is congruent to 0 modulo 17, again, then obviously k to the power of 561 is congruent to 0 modulo 17. No problem there. And if it isn't, then again, by Fermat's-Little theorem, k to the power 16 is congruent to 1 modulo 17. And now I will raise both sides to the power 35, because 16 times 35 so happens to be 560. And now I will simply multiply both sides by k. And in every case we see that it holds. So indeed, the only solutions, the only possibilities, are 11 and 17. So P equals 11, Q equals 17, or we can change them. It can be also true that P equals 17 and Q equals 11 by symmetry. And that's it. These are the only solutions in primes of our problem. Very nice problem. So remember, main takeaway from this video, if group is cyclic, sometimes it's good to use the fact that it is cyclic. So it was very crucial, because this whole reasoning was based on these two divisibilities, this one and this one. They were crucial for us. And we have established them by choosing elements U and V of correct order. So, yes, very nice problem. And again, as you have seen, verification is very important. So I get 11, 17, but I need to verify them, and I did. And yes, that's it. A very nice problem from Romania, as always. Thank you for watching. I wish you a nice day, and I will see you next time. Goodbye.